finally I'm coming also to the other course we are working on together, so MDA 102, and in this week we have to, or we want to have a look on what really the reals are and what is the complex plane and how to handle those. So let me start with the reals themselves. So similarly as we did with the scalars in general, so we can just list a number of axioms, and all the axioms will be exactly the properties we want to claim to be true, right? And of course we want to see that the reals are the scalars, and actually it's just the most complete set of axioms, because we also want that there are the inverses for multiplications for all a's. There is this distributivity as in each ring, and on top of that we expect that there is the ordering relation, which is a total order. So we can say for every two reals we can say which one is bigger and which one is smaller, or it might happen that they are the same, right? But that's just special. And we want that the order is compatible with the addition this way. So we add the same thing to the left and the right sign in the inequality, it must hold true again. And we also want that multiple of two positive ones is again positive, right? So that's very important. But all these are true for rationals. So rational numbers would satisfy all the first 12 axioms. The complex numbers, not, right? So there is no ordering on the complex numbers which would satisfy this, and this can be proved. We shall come to that soon. But what we want to see is the last property, and the last property says that whenever we take a non-empty set which is bounded from above, then there must be least such bound, and that's what we call a supremum. And that's the very important property of the reals, which means that what we actually are doing is we imagine the reals as having the real line of this kind, where here is 0, here is 1, here is 2, and so on, and there are all the rationals are somewhere there. So all of them are somewhere there, but there are also the reals which are filling the gaps, because as you may imagine, so the square root of 2 is not a rational, so we came close to that. But what we can do is we can just consider all the a's such that a square is less or equal to 2, and according to the axiom R13 we may simply claim that the supremum of this set of a's will be what we call the square root, and that's exactly how we shall proceed. So that's easy, except we don't know whether such guys exist. So how could we know that there are the suprema there? So we have to build the real numbers, and I will not go into details. In the end of the semester we shall do the same in much more generality at the level of what we call metric spaces. But here just a indication how this would work. So that's not that difficult. What we imagine to do is we first, well, let me come back here first. So I don't have to come back to complex numbers, that's okay. But let's notice that for the complex numbers we have the conjugate number and the multiple of x times x bar, or z times z bar, is giving us exactly the distance of the point in the plane from the origin. So it matches nicely what we did in the other course this week. So this is the formula. So we have got the absolute value, right? So that's the definition of how we understand how far the points are away each from the other in a plane. So we take the difference of those and we say that the absolute value of the difference, which is a complex number, right, would be just it. And we know that the absolute value always satisfies the triangle inequality, and that's the absolute basis of all the analysis we shall be doing. All the estimates, all the changing infinitesimal understanding to real understanding will be based on such type of estimates, with triangle inequality being absolutely the most important one. And before I can explain how to build the reals, which is the task we have to go for, we have first to understand what does it mean that there are the gaps there, right? And I think it's much easier to imagine this in the complex plane, although the same arguments or imagination works for a real line as well. And that's what we mean by claiming that a sequence of points, so we have sequence of points, so K is either reals or C, so complex numbers, or perhaps also rational numbers, it's okay. So all three are possible for my K here. And imagine that we have such a sequence which has the property that whatever small epsilon I take, so if I tell how small I tend to be or want to be, I can always say that all the numbers AI, AJ in the sequence will be closer than that except a finite number of them. So in the complex plane, you can imagine you have a set of points like the picture here, and you know that whatever small coin you take, so it could be as small as possible but not zero, right? So a coin, you can always put it to your screen so that all of the points are covered by the coin except a finite number of them. And that's what we call a Cauchy sequence. And you see, if I just shrink the coin and I go to the resolution of the screen, so I would say that that's the limit, that's where all the points converge to. But actually, it possibly doesn't exist there, like with the square root of 2, right? So I can just have a sequence of numbers which would approach the square root of 2 from below, just taking bigger and bigger a's in rationals. But there will be no rational number there, which is the square root of 2, right? And therefore, in the rational numbers, such a sequence will not have the limit point, right? So this is the Cauchy sequences. And then, of course, this suggests how to define the convergence of such a sequence. So if there is an a fixed number, either complex or real or rational, don't care. And we know that if I tell how close I want to be, then I can ensure that all but finite number of them, so it means that there is some capital N, so that for all the elements in the sequence, after the nth one, it will hold true. Then I say that the sequence has got a limit, and the limit is simply this. So it's that simple, right? And now, of course, every convergence sequence is a Cauchy sequence. That's easy. But what's not easy is this claim. Every Cauchy sequence of real numbers AI converges to a real number A. And this is the consequence of the supremum axiom. You can go through the proof and see yourself. And there is an obvious corollary that the same will hold true for complex numbers. Again, just give it some time and look why I can claim this. But this doesn't solve our initial problem I mentioned. So how to understand the existence of the real numbers, right? And here it's a very simple way how to go there, and it's pretty the same thing as we did with rationals being built from integers. So we simply told, well, what about the quotients of integers? So let's take the couples, and the couples of the integers would represent the quotient of them. And if there are different couples giving the same quotient, then we call them equivalent, and the equivalence classes will be the rationals, right? What we do now is we do the same with the reals. So instead of taking quotients, we shall take Cauchy sequences of real numbers. So imagine we have got simply the so a real number A will be something which will be a 0, a 1, and so on, and it will be a Cauchy sequence, and it will be an equivalence class. So A is an equivalence class of those, and it's obvious how would you say what's equivalent, right? So the two Cauchy sequences are equivalent. So if I write a B, which would be B0, B1, and so on, if I know that if I take AI minus BI in absolute value, then this should go to 0 with I going to infinity, right? And we know already what it is. So this is the definition of equivalence on the Cauchy sequences. And of course, if it happens that A should be a rational number, I didn't say that actually whatever is here is in Q. So it's Cauchy sequences of rational numbers, right? And of course, if A should represent a rational number, then I can take a constant sequence of A up to infinity, and that will be the canonical representative, nice representative of my rational number. And if I want to represent the square root of 2, I can't do it this way, but I have infinity of possibilities how to approach it by rational numbers, and all of them will be Cauchy sequences, and all of them will be equivalent, because if they approach the same thing, this property must hold true, right? So this is rough indication how to build the real numbers. Of course, part of the story is easy, and it's indicated in the text here. You can simply define in an obvious way the addition, the multiplication, the ordering, everything works fine. But the difficult point is that if you just then look at this new guy, this new real numbers object, then you have to verify that the supremum axiom will also hold true. And we shall come to that in much more general approach in the end of the semester. And it will also follow a nice say in mathematics, which is quite often true. If you find something too complicated and too difficult to understand and handle, try to make it more general. Sometimes it works. We shall see. So now let's leave this and come to the other half, which I promised, and that's what I called topology of the real line and complex plane, right? So we've got now, forget about the construction of what the reals are. Believe we've got the real numbers satisfying all the 13 axioms. We've got the complex numbers which are built from the reals, the way we know. And let's have a look how we can view the complex plane real line and what are some important properties and concepts there, and we call it the topology. And topology talks usually about the open sets and closed sets. So what are the closed sets is easy to see if we define what is a limit point of a set. And limit point of a set, vaguely told, is simply every point to which you can converge by the elements from the set, but you have to assume that the elements will be different from the limit point, right? So if you have one isolated point, then it's not a limit point. But if you then converge to any point by some sequence inside of your set A, then independent of whether this limit point is inside or outside of A, it will be called limit point, right? So that's the basic concepts. And closed sets, as you can imagine, is the sets which contain all their limit points. So you can't simply converge with points inside of the set and then finally stay outside. That wouldn't be closed, right? So it's just why it's called closed. And The open sets are the complements of closed sets, and it's easy to see that actually an open set is something which with each point inside of the set contains also some small neighborhood, and the neighborhoods are built this way. So you simply take some number delta, which is a positive real number, and you take all the a's, all the x's close to a enough, right? And you have a strict inequality here, and therefore it's open, right? And open sets are those where each point is in with some neighborhood. And the language of closed and open sets is extremely useful because it's something you can imagine nicely. In particular in the complex plane, it's easy to understand this O delta. It will be a small circle, well, the interior of a small circle, whereas in R3, on the real line, it will be just a plus minus delta interval neighborhood, right? So that's very straightforward. There are a few properties here, and one of the most crucial concepts in mathematical analysis is the concept of the compact sets, and it's related to bounded sets. So bounded means that the whole set of yours in the complex plane or real line sits in one huge, possibly very huge circle, right? So inside of one big circle, and then we call it bounded, right? So you can imagine that it's then written this way for some constant r. Compact is something which is bounded and closed at the same time. That's one of the many equivalent definitions, but this is the one we can use here. And there are some more concepts, so I will not go through all of them, but here is a nice theorem which summarizes all the things together, right? So it says that a non-empty set is open if and only if it's a countable union of small open intervals or big open intervals, so countably or finitely many open intervals. In C, if it's finite or countable union of small disks. Every point is always either inside or at the boundary. Boundary means that in each neighborhood there are points from both A and its complement, right? Every boundary point is either a limit point, so you can converge to that from inside of A, or it's an isolated point. Isolated point means that in a neighborhood there is some neighborhood that there is nothing else but this point from A there. And compact, the most important two is properties here. Compact is if and only if from every sequence in A, you always can find a subsequence which converges to something inside of A. So you see, that means compact. So you can't run infinitely towards some one or other side of the real line, or further and further from the origin in the complex line, the complex plane. And so it means that, of course, you can have, for example, a sequence where all the even numbers will be even components will be 0 and odd components will be 1, right? And then it can't have a limit. But there is the subsequence which does, right? So that's the property of A. And what we say is if something is closed and bounded, then each sequence will have a subsequence which converges, right? So that's very good. And this is also even more important maybe, so I wanted to say also important. So a open cover of a set means that you have maybe uncountable many, so any set of open subsets, and their union would involve A inside. So it's covering A in this sense. And the claim is that a set is compact if and only if each open covering includes a subcovering which is finite, right? So I can always find only finite many of the circles or of the disks which cover a compact subset in a complex plane, or the same on real line. And the main power of that is that you are sure that you can choose some of the given open cover. It's not that there exists some finite cover, but from each open cover you can choose your subcovering. So that's extremely important. And this is about it, what I wanted to say in this particular. You see, this is a more complicated proof, so for those who want to have some adventures and test themselves, please try to go through. So this is no way simple, right? So if you feel failing, don't worry, just skip the proof. It's enough to understand the content of the theorem by now, and you will see how quickly your absorption capacity will grow, and you can come back to that later once you need it. Right, so that's it. That's it for this time. So thanks.